Well, quite late in getting this out. I'll just have you guys watch it in class. So we move into quantum mechanics, and with quantum mechanics, this leads us to Erwin Schrödinger's idea of his approach, understanding kind of the wave and the particle nature, combining together, incorporating into this kind of this scatter plot of where the electron is 90% of the time. So kind of bringing together a variety of different concepts all into one idea. And this idea is known as quantum mechanics. We've kind of led up to this point. And so quantum mechanics gives us this idea that we have a wave equation designated with the Greek psi symbol, and the square of the wave equation gives a probability density map of where an electron has a certain statistical likelihood of being at any given instant in time. So this is the idea that statistically the electron is going to be in this area 90% of the time. Now we could go 100%, but that volume ends up being it's not functional for how we want to interact with atoms, and so we pare that down, the electron cloud, to being 90% of the time where the electron is. So when we move away from the idea of orbits into this idea of quantum numbers, we call those different wave functions orbitals, and they define a specific region of space around the nucleus where the electron exists, and there's energies associated with it. Each orbital describes a spatial distribution of electron densities, and we've looked at orbitals a little bit in the past. So, and each orbital is assigned several different quantum numbers, and those quantum numbers basically gives us the address or the exact location or the best location of where different electrons are, or we assign where they are. They definitely might change position or alternate which position they're in, but it gives us a way to define their locations. So the first quantum number is what's called the principal quantum number. It's indicated by the letter N. Okay, and it describes the energy level on which the orbital resides. So when you think of the periodic table, the quantum number, the principal quantum number, is defined by the period that would be found on the periodic table. So like period 1 would represent the first principal quantum number, or energy level number 1. And so the values of n can only ever be greater or equal to 1. So 1, 2, 3, 4, 5. We don't have any half numbers or negative numbers when it comes to the quantum number. The next one is the angular momentum quantum number, which is indicated by L, and the quantum number defines the shape of the orbital. So this is L, or the angular momentum quantum number, defines, is it an S subshell? Is it a P subshell? Is it a D subshell or an F subshell? So that is defined by the angular momentum quantum number. And so values can be integers ranging from 0 to n minus 1. So if the energy level is 1, so if n is equal to 1, then therefore the L can only be equal to 0. But if n is equal to 2, then you can have variety there. So we'll look to the next one to kind of see this idea. So the value of L, if it's 0, it's S. If it's 1, it's P. If it's 2, it's D. And if it's 3, it's F. Next, we have our magnetic quantum number, or M sub L. And the magnetic quantum number describes the three-dimensional orientation of the orbital. So when you think of the p orbitals, we have p orbitals going up and down on the y, the x, and the z axis. And so the allowed values of M sub L are integers ranging from negative L to L. So if L is 0, then there's only 1. There is no range. There's just one orbital space. And then if n is equal to 2, then you can have 3. Okay, so this is where we get those specific orbitals where we're going to fill electrons in there. Therefore, on any given energy level, there can be up to 1 s orbital, 3 p orbitals, 5 d orbitals, and 7 f orbitals. So orbitals with the same value of n form a shell, so you have like 1s and 2s, same, very similar, and then 2p, 3s. So we're just kind of expanding on these, what we call the subshells. So different orbital types within a shell are subshells. So let's say in the second energy level, we have 2 subshells. We have the 2s and the 2p. For the third energy level, we have, or the third shell, we have 3 subshells, the 3s, the 3p, and the 3d. So the s orbitals, the value of L for s orbitals is 0. The shape is spherical. The radius of the sphere increases as the value of n increases. So it's just that idea as we go down the periodic table, the s subshell gets larger. So when observing it, like the probability or location of the electrons um, near the nucleus, you can see kind of this breakdown of where the 1s would be, where the 2s set of electrons, where the 3s, and you see how they kind of get spread out as we get further from the nucleus and we get this larger space out of it. But there are these defined nodes where the electron for sure is not located, and those allow us to kind of separate out the different subshells. So when we move to the next set, we've got the p orbitals, and so this is where the L for p orbitals is 1, so 1, 0, -1, and they have these 2 lobes going off on all 3 axes. And then you have the d orbitals, which I find, well, I just enjoy them. I like that donut one in the middle or down at the bottom because it's just odd, but that's what the statistical math tells us where the electron is. And remember, keep in mind, all of these orbitals are overlapping each other. The larger and larger the atom becomes, there's more space around the nucleus where the electron can exist. And so these are all kind of laying on top of each other, but they're getting larger and larger, so so more electrons can fit around that nucleus properly. So then when we move with the energies of the electron, or of orbitals, the lowest energy is the 1s, and this kind of defines like the way that the orbitals fill when we talk about like, oh, what's going to be the orbital filling pattern for this? Well, the lowest energy level is where the electron is going to be. So it starts out going into the 1s first. So for one electron hydrogen atom, orbitals on the same energy level have the same energy. So that is, they are degenerate, meaning, so let's say we excite an electron from hydrogen. Well, that electron is going to be in the 1s, and it's going to jump into the 2, the second energy level, but it really can go into the 2s or the 2p's because at that point there isn't kind of this hierarchy when there's just one electron in the system. Now it becomes more complex when in a multi-electron system, so because the electrons are repelling each other, and so then when electrons get excited, there's a more complex levels where the electrons will jump from one level to another. So in many electron atoms, orbitals on the same energy level are no longer degenerate, meaning as we fill or as electrons get excited, they can get excited or fill in a particular order according to which spaces are the lowest energy for electrons to go into. Excuse me. Right, the next part is the idea of quantum spin. And this is the idea that electrons either have what we refer to as an upspin or a downspin. And what that means is that, so we've talked about three quantum numbers, and the last quantum number is the spin quantum number. And this is the idea that when we fill orbitals, you fill electrons going in one direction. So this is where we fill with arrows. And then we fill going the other direction in opposite arrows, because the electrons are all negative, so they're going to be repelling each other. And so the only way for them to exist in the same orbital space is if they are spinning in opposite directions in that region. And so this is the idea of the fourth quantum number being the spin quantum number, and it's either spinning upwards or downwards as we model it. So the spin quantum number has only two allowed values. That's plus 1/2 and minus 1/2 when we place it. And so this is, and then the Pauli exclusion principle is the idea that no two electrons can have the same energy, meaning they can't have the same four quantum numbers. So no electron can have the same four quantum numbers, similar to like having, a specific mailbox that, let's say you have a post office box, only one electron can exist in with and have the same mailbox number. So no two electrons in the same atom can have identical sets of quantum numbers. All right, and then I think we're going to pause there, and that should do you for tonight, or